So both piecewise constant regression, the step functions, and polynomial, they are special cases of basis function approach. As I mentioned, the basis function approach transforms the features. B1, B2 are fixed and known. These are functions for polynomial. These are just xi to the power of j. For piecewise constant, it's these indicator function, and in general people play a lot with these functions to capture nonlinearities. Okay, what we are interested in is splines. Okay, and regression splines, and we start with piecewise polynomials. Piecewise polynomials mean that we say, okay, this is the relationship is nonlinear, so let's just split the interval, and within each interval fit a piecewise cubic function. Okay, so here we have a cubic function, that means a polynomial of degree 3. Here, for this interval, we are fitting a polynomial of degree 3, and for this interval, we fit a polynomial of degree 3, and this is our model. So instead of fitting a high degree polynomial over the entire range of x, piecewise polynomial regression, in this case piecewise cubic polynomial regression, involves fitting separate low degree polynomials over different ranges. Here is this range and this range. Now, what is the problem here? What is the problem we see here? The problem is here that we experience a jump. We see a jump here, and this doesn't make sense. Why should at age 50 we have this discontinuity? Okay, and in order to address that, we can fit a piecewise polynomial with a constraint, and the constraint is that this breakpoint is known to be a knot, that at this point the curve must be continuous. So it can be an added constraint. Remember, when we are fitting, you can always add these constraints. And by adding this constraint, this is what we get. Now, what is the problem here? Well, you see this V shape here? So continuity is not sufficient. Continuity is not sufficient. It's better, but this is still unusual. So what we do is we can add another constraint, and that constraint is that the derivative is continuous. And then we have a cubic spline. So just to recap where we started. This is where we started. There is no constraint here, just a piecewise cubic. If you add a continuity constraint, then you will get this one. If you add a continuity constraint also to the derivative, then you get a cubic spline. And it makes sense. We want the piecewise polynomial not only continuous at h50, but also smooth. And smoothness means that the derivative is continuous. Okay, and spline stands for a smooth polynomial, piecewise polynomial regression. Okay. Okay. And here we have a linear spline. Okay, so splines, there's a lot of detailed math that I will just skip. That detailed math is more useful for a researcher. For somebody who wants to use it, it's pretty straightforward in R, and that's something I will do at the end of this chapter. Okay, so here we have weights. Blue is a cubic spline. And then we have the confidence bands, so the confidence intervals, and we see they're wide. And these are the knots at these points. And now we can also have a natural cubic spline. And the natural cubic spline is a cubic spline with an extra added constraint. It's the boundary constraint. And the constraint is that the function, the spline, needs to be linear at the boundary. And it's the objective here is to add more stability at the boundaries, because at the boundaries we have less data, and because we have less data, the spline can behave erratically. And as you can see, since we fit a line in this interwall, the model is simpler and the confidence band is narrower. Okay. Now a recurring question is, how do we know where to place these knots, and what are the locations? Okay. Here, the way it's done, these locations were chosen to be the 25th, 50th, and 75th percentiles of age. Okay. Now, the more knots we have, uh, the more flexible the curve. And one way to choose the number of knots, you can add more knots in between these. It's typically done using cross-validation. And yeah, so that's essentially what's going on here. For example, degrees of freedom here. So what are degrees of freedom? The degrees of freedom are proportional to the number of knots. This is a squared, mean squared error for the spline. We have a natural spline, and then we have a cubic spline, and this is 1 degree, means 1 line. Then boom, we come down, down, and then somewhere here, I mean, this is the minimum. These two don't show a big difference. And it seems like 4 or 5 degrees of freedom, I mean, degrees of freedom of 6, 7, here it's 5, are attaining the minimum cross-validation error. Okay. So, polynomial regression or splines. Look at this example, wage. Polynomial regression tends to behave erratically at the boundaries. This is not just particular to this data set. It typically happens. Polynomial regression is actually rarely used in practice, and in textbooks it's introduced as one of the first methods, so that we can build other methods from that. But in practice, it's rarely used. Again, here in the middle it does well, but at the boundaries it behaves erratically. Now, smoothing splines. Let's talk about smoothing splines. Okay, so far, everything that we talked except for polynomial regression, specifically when it came to regression splines, something that was fundamental to what we were doing was specifying a set of knots. The knots that created intervals, within which interval we would fit a separate regression function. So whether it's polynomial or whether it's a step function, that doesn't matter, but the key was that we had knots that created intervals, and the number of knots and the location of them. The number of knots we could choose by cross-validation. So yes, and the location was to some extent arbitrary. We had some rules, but we had no principled way of approaching it. Okay. So now we want to approach this problem differently, and to start from the very beginning, what we really want is that we have these data points, these yi's, and then we have this, we want to find a function. So we have yi and xi, and we want to find some function g that is close to yi. We want this residual sum of squares to be as small as possible. Now, in other words, we find the function g such that this is as small as possible. We call it g hat. And if we don't put any constraint on g, then we can always make this 0 by having g of xi being equal to yi. We can have g hat xi being equal to yi. We can make this as small as possible. In other words, this g hat interpolates all the yi's. And this function is overfitting the data. It's just too flexible. So what's the problem here? The problem is that we have not forced g to have any specific constraint. Remember, in the smoothing spline, one of our constraints was that at the knots there is some continuity, or the derivatives are continuous. Now, let's imagine we want to find the g, we want to have a constraint on this optimization problem. We want to find the g that is as smooth as possible, yet it minimizes the residual sum of squares. Now, a question that arises is that how can you formulate smoothness mathematically? How can you do that? Formulate smoothness. How can we measure whether G is smooth or not? Well, and one of the ways is to use the second derivative. Remember, derivative, the first derivative is the rate of change. The second derivative is the rate at which the derivative is changing. Okay, so what is this? This is integral. These two, they indicate the second derivative. This integral is just summing all of these derivatives. Okay, there's some problem here. There needs to be a square. There needs to be a square here. Okay, so it's squared. It will show up in a second. Okay, so this term is a penalty. It measures the model complexity. If G is bigly, if G goes up and down a lot, the second derivative would be large, so the square of it would be large. So when we integrate it over the interval, this will be a big penalty, big model complexity. But this is a measure of roughness. This is a measure of the roughness of the function G. And you can think of the integral notation as a summation over the range of t. So simply put, this term here is a measure of the total change in the function in the derivative. So if G is very smooth, then the first derivative will be constant and the square of the second derivative will take a small value. On the other hand, if G is wiggly, if G is jumpy, if G is variable, then the first derivative will vary significantly and the integral of the square of the second derivative will take a large value. So again, this term here quantifies how smooth the function is. And we want a function that fits the data well, but it's not too wiggly. And the balance between these two is determined with lambda. If lambda determines the trade-off. If lambda is 0, then we don't have this term and we end up with just G hat being equal to yi. On the other hand, if lambda is infinity or is large, is not, let's say not infinity, becomes very large, then G becomes very smooth, perfectly smooth, and in the extreme case, it will be just a straight, not perfect, it will be just a straight line, and essentially it will be just a line that it would be as if you're fitting a simple linear regression model. So if you set lambda to infinity or a very large number, the G that you get is almost like a line, and if lambda is small, then you get a very wiggly function. So it's possible to show that mathematically, which is beyond the scope of what we're doing, that the function that minimizes this is a smoothing spline with knots at the xi's. Okay, and yeah, so that's the mathematical part. So we have the loss plus penalty, and this is very similar to what we saw and did with Lasso and Rich. Okay, how do we choose lambda? You can do leave one out cross validation, and it turns out that there's a simple formula for it. I skip the math, which we'll see in our example of how to do it. Here's the wage versus age example. Degrees of freedom is 16. Remember, degrees of freedom is different from lambda. Degrees of freedom is inversely proportional with lambda. So the larger the lambda, the smaller the degrees of freedom. The smaller lambda, the larger the degrees of freedom. And if you choose the degrees of freedom or equivalently lambda using leave one out cross validation, you get this blue curve. If you use 16 degrees of freedom, you get the red curve. They're slightly different, and yes, this is essentially what I wanted to get across. Okay. There's another method called local regression. I don't want to spend a lot of time on it. I just want to put it out there. I will kind of skip it, but what it does, excuse me, what it does is that to predict any, and essentially the underlying curve, it uses all the data points around the point. So it's like a kernel smoothing method, if you have seen it, where you have to choose the bandwidth of the smoothing of the kernel. Okay, so I may show an R example, but this is as far as I want to talk about it. Let's just skip this. Okay, this is something I like to talk about. Okay, so generalized additive models. So this is the multiple linear regression model we saw many times. GAMs just use the same sort of representation, except that instead of having these terms that are added, these are linear terms in each feature, they use different functions. So we have a function for the first covariate, a function for the second covariate, a function for the third covariate, and these are just added, and these are separately fitted, and they are fitted such that they are, you can think of them as being, so we use a smoothing spline for this, we use a smoothing spline for this, and we use a smoothing spline for this, and then it's interpretable because then we have these different components. Okay, so yes, for example, we want to predict wage based on years, age, and education, and we believe that wage can be expressed as some sort of function of year. We don't know what that function is. Some sort of function of age and some sort of function of education. So our underlying modeling assumption is that this is additive, that there is no interaction, but we don't necessarily assume that the relationship is linear. Okay, so you see the difference? We relax the linearity assumption. We still assume there is no interaction. And we allow that nonlinear relationship to be anything. And we can use a spline, for example, to fit it. And then things become a little bit more interesting, that we see that with the component in wage that depends on year is increasing with year. It's increasing with age, but then it goes down, and it's increasing with education. And education is a qualitative variable. That's why we have these less than high school, less than college, higher than college. This is really nice because it's easily interpretable. Now you may ask, what are these functions here? These are natural splines with 4 and 5 degrees of freedom. And then here we have a smoothing spline with 4 and 5 degrees of freedom. We see the qualitative behavior doesn't change. Excuse me. Okay, so GAMs are really nice because they allow non-linearities. They don't make any assumption about the non-linearities. So we can capture behaviors that we did not expect or we didn't know in advance. They're interpretable because they are additive. The only problem is that that interactions are hard to capture. Okay. All right, so let's do some examples to make these all these topics, these concepts more concrete. Okay, so let's do a simple polynomial regression for the wage data. Okay, so what is happening here? We load the wage data, we fit polynomial of age 4. What does this mean? It creates a 4th degree polynomial. So instead of writing the long formula with powers of h, we can just use this. Okay. Now we could do fit alternative and equally write age to the power of 2 plus age to the power of 3 plus age to the power of 4. And then we can get these coefficients. Okay. These are the estimated coefficients, right? And then here we can do this again. Okay, so we have to use the I. This I is different from the indicator function. This is not the indicator function. This is a different way of fitting a polynomial of degree 4. And now you may ask then, why are the coefficients different? And the reason is that when we use this poly h4, it gives us a basis of orthogonal polynomials, which essentially means that each column is a linear combination of the variables of h, h2, h3, h4. Just look at this. H to the power of 4 is huge. It's going to be a large number, much bigger than h. And that's why the estimated coefficient is proportionally smaller. So the scale of h4, h to the power of 4, is significantly bigger than the scale of h, and therefore the estimated coefficient is much smaller. So now On the other hand, if you use orthogonal polynomials, then they all are in the same scale, and therefore the estimated coefficients are on the same scale. Okay. Now we could have gotten the same results here by saying just raw. True. Let's see. So, okay, let's look at this. X can be this, right? So X is this. This is our design matrix. These are ages. This is h squared, h to the power of 3, h to the power of 4. Okay. And this is just raw, right? This is exact. These two let me see if this runs. Yeah, these two are doing the same thing. Okay. Now, if we take this raw away, then first of all, the coefficients are standardized. Second, these columns are orthogonal. How can we see this? T, X, X. You see, the off-diagonal terms are almost 0. The diagonal terms are 1. That means that, for example, another way of seeing this is, let's say we take the first column, all the rows, zero. If you do this, sorry, 1, 0. But then if you do 4 and 4, it's 1. When it comes to prediction, it doesn't matter which one of these models you use. They will give the same prediction, but the estimated coefficients will be the same. Okay. Now another way of doing this is you can do it using cbind. Okay, cbind is a function that we have used before, or I don't know, maybe not, for building matrices from a collection of vectors. And any function call, such as cbind inside a formula, can also be used. So here, yeah, we get the same result. So these three are doing the same thing. Now, let's say we want to make predictions for all ages. Okay. We want to make predictions for all ages. We have the age limits. which is range of age, (18 to 80). And then we create a sequence. So age goes from 18 to 80. And let me just do predictions. Okay, so let's call this y hat, and we can just do predict. Take the fit, new data, standard errors we want, yes, true. So y hat, I see. Let's just call this pred. Okay. Now we could do the same thing, just so you see that, and then we can get the same thing. So we have pred 51.93, 58.49. (51.93, 58.49). So what I wanted to get across is that the predictions are going to be the same, regardless of which of these you use. Even if you use this one or any of these three. I mean, these three are exactly the same models, obviously, but this one is just formulated slightly different, but it gives you the same result because these columns are just linear combinations of the columns used here so that they are orthogonal. Okay. Now, how can we plot the results? Okay, so this is the plot that we wanted to create. What I did was we got the predictions. Let's just ignore this. Here we get the predictions. We give the new data, which is everything from 18 to 80. Then we create the standard error bands, meaning the upper and the lower. The upper is the prediction plus 2 standard errors. The lower band is the prediction minus 2 standard errors. And then we plot the raw data. We give it a title. We draw the prediction. We give it a color, a distinguishing color. And then we add the confidence interval bands, upper and lower bands, SE band, which we defined here, to get this figure. mar and OMAA arguments to pair. They allow us to control the margins of this plot. Okay. Okay. So this is how to do polynomials. Let's I will skip the step function because it's not really that useful in practice. Okay, so I jump immediately to splines. Okay, so how to do splines. Okay, as I said, for the rest of this lecture, I will focus on smoothing splines and generalized additive models, because these two are mostly used in practice, and I think they will be useful for you in the future. So in this part, I am just plotting the data, and I'm titling it. I fit a smoothing spline, wage versus age. I arbitrarily choose the degrees of freedom 16. For the sake of comparison, let's just make it actually larger. Let's make it 25. And here I'm saying choose the degrees of freedom using a cross-validation. The optimal degrees of freedom is 6.8. Fit $df gives us the optimal degrees of freedom. Then I'm going to plot the fit. This is the degrees of freedom is, what was it, 25. Let's make it even larger, 45. You see, when you increase the degrees of freedom, the curves becomes wiggly. The optimal degrees of freedom is 6.8. So this is a proper graph. Horizontal axis, vertical axis, title, legend. We know what each color is supposed to represent, and yeah, that's great. So you see the difference. So this is really easy to use. Okay, next we go to generalized additive models. Okay, now for fitting a generalized additive model, we have to call the GAM library, and what we are saying essentially here is that we want to fit wage to S. S here is a smoothing spline. Is a smoothing spline, and we say so year is a smoothing spline with degree 4. Here we use a smoothing spline with degree 5, and education is categorical, so we leave it as is. And that's it. So now you may say, how do we pick the degrees of freedom here? We can do we can write an extensive cross-validation function over the degrees of freedom for year and age, and this is exactly where what you learned in cross-validation is useful, because at least I am not aware of a cross-validation function written for this purpose. Maybe there is, but now this is an example that even if it isn't written by somebody, you can easily, I mean, it takes a little bit of time, but you can write a cross-validation routine that goes over the degrees of freedom, so you can select the optimal degrees of freedom. So let's just, yeah, so that's that. So we run this, and then we can also make prediction using this object. We give it the wage data, and then we have our predictions. We have the standard errors, and we have our fit. And here are the components for year, age, and education. So in this chapter, we learned how to go beyond the linear models. We talked about polynomial regression, step functions. We talked about basis function, piecewise polynomial, and generalized additive models. So you learned the concepts. In practice, I think mostly smoothing splines are very useful and they are easy to use, and also generalized additive models. Okay, and I think this summarizes this lecture, which is based on chapter 7 of the ISLR book.